Well, back in the late 17th century, you're aware that Sir Isaac Newton was busy working his gravitational force laws and developing the calculus, but he was doing more than just figuring out how long it would take an apple to fall off a tree. He also developed many applications, one of which was the root solving method that bears his name and later simplified by Dr. Raphson. What this method is going to do is improve on our two-point system that we used in the bisection method and its associated derivatives. Instead of that, we're going to pick one point as a guess. That guess we will have to supply. And Newton will take over from there and converge into a root at astonishing speed in most cases. We're going to be using a tangent line to a curve where the slope of that tangent line it will be the same as the derivative of the function that we're trying to find the root of. So let's just take a look, see how that plays out, and we'll draw a little picture here to help explain it. This curve will represent our nonlinear function that we're trying to derive the root, or at least a root of interest. We will guess where that root is, maybe a good guess, maybe a bad guess, and we'll call it x0. From x0, we will determine f of x0, which is the point straight above it that lies on the red curve, on our nonlinear curve. And we will force a straight line to come right through that point. Now, to make it tangent, we also have to make sure that it has the same slope as the curve at that point. But that's easy to do because the slope of the curve is the derivative. So we'll set up a straight line, y equals mx plus b, m being the slope, and equate that slope to the derivative of the function at that point. B is going to be the intercept, which is down here. That point we will need to complete the line, but it's not really what we're after. What we're after is where this blue line, where this blue tangent line hits the x-axis. That would be the root of the linear equation, not necessarily the root of the curve, but hopefully close, or at least closer than where we started. Upon doing that, we can very easily predict where the blue line hits the x-axis. Straight lines aren't hard to manage. We will call that value x1 as being our next approximation of where this root actually lies, which we're calling r. x1, now probably being superior to x0, could be plugged right back into our root finding system, and we could start it again, coming up with yet a better approximation as represented with this black line on where that root goes. Now you can see visually that that seemed to be a great improvement over the blue line, and in fact it typically is. If you do the whole process again, you'll come up with an x2 that's sitting quite close to the root, and by the time you run a tangent line from that point, you're going to be almost dead on. So just graphically, this method seems to have a lot of appeal. So let's go ahead and do the algebra and see where it goes. Okay, let's bring back our equation again. We have y equals the slope times x plus b, and our slope's easy to get because we just take the function we have, differentiate it, and plug in the initial guess value. This general line must apply to every point on the line, including x0 itself. So if I plug in x0 here, then the y at x0 must be exactly equal to f of x0. I'm constructing it to be that way. So let's write that down. F of x0 will be exactly equal to that slope, evaluated x0, times x0 plus this b-intercept. Now I don't know the b-intercept yet. I do need to find it. But it's sure going to be easy to find because everything on this equation is known except for b itself. So all I really have to do is subtract f prime of x0 times x0 from both sides of the equation, and I've got myself my b value. So here we have constructed b just in the manner we described, and we'll plug that back into our original linear equation. Now we could simplify that a little or make it look a little nicer by combining the two derivatives of x0 together, and then you would have f prime of x0 times a deviation of x from x0. So this is what it would look like if we just combine those two terms together, and all you have left on the right is f of x0. Now remember, this relationship is approximate. It's not exact. F of x represents the true values of x evaluated through the function, where this is a straight line that approximates better and better as x gets close to x0. Well, if we take our root r and stick it into this equation, it would be very nice if that straight line was reasonably close to 0. After all, r is the root for f, and we're hoping this line comes somewhat close to approximating the function. I don't know how far off it is, though, because I don't know how good a guess I started with x0. So maybe it would be even better to replace r with a different variable name called x1. x1 will be wherever that line did hit the x-axis, and we're hoping x1 is closer to r than x0 was. So let's go ahead and do that. Instead of the root, we will use this term x1, and now we can use the equality sign. So 0 is equal to the exact same formula, but plugging in x1 as the actual position of where the line hits the x-axis. So that's just really a matter of some simple algebra. We can solve for x1 by bringing f of x0 to the other side of the equation, and then dividing both sides by f prime of x0. By the way, if f prime of x0 is really close to 0, that might create a problem, and we'll come back to that later. But if we do it anyway, we'll have x1 minus x0 equals this ratio, and we end up fairly simply coming up with a formula for x1. This is almost certainly a better approximation than I had with x0 to begin with. And you might say, well, now that I know x1, why didn't I just pretend that was x0 and plug it into that formula itself? And I think that's really a good idea. So we'll do that. We'll use the exact same formula, plug in x1 everywhere we had an x0 before, and call the new result x2. Well, if we did it once, why couldn't we create an x3? If x2 is even closer to the root than x1 is, let's plug x2 everywhere we see an x1 and continue doing that until we realize we have an iterative formula that should converge rapidly into the root. So this is the way we express the Newton-Raphson algorithm for one variable, and we have a number of iterations that we indicate through n. There's not a whole lot left to do with this thing other than put it into pseudocode and see if we can't develop it into a MATLAB program. So let's copy the iterative formula that we had before and revise our algorithm that we've looked at to be really simpler. We still need a tolerance. We'll make this one 10 to the minus fifth. We still need a counter variable. We still need some initial guess of where the root is, but we don't need two like we did before on the bisection method. We'll set up a loop, and I'm using repeat until, but when you're doing this in MATLAB, you'll have to change this to a while loop. We still have an interest in preserving the previous calculation that we did in each loop. So on the first pass, x previous will be just x0. And then just put in your formula, the Newton formula, where x sub n plus 1 is equal to the difference of x sub n minus this ratio, and overwrite the value that's in x sub n plus 1. How long should we do that? Well, we need some stopping rule. We could use the relative error that we looked at before. Well, you take the last two values, take their difference and their absolute value, and divide by the absolute value of the most recent calculation. You could ask the program to stop when that relative error got small enough, or you could alternatively look at when the function value is close to 0, since that's the whole point of the thing. In either case, you probably only want to use one or the other of these, not both, but I've just put them there so that they're documented. But you might want to have this restriction on n at least until your algorithm has been debugged, and then you might get rid of that later. So this is a much simpler, much shorter algorithm. We're going to find it even works a whole lot better than the ones we've talked about so far, which is really nice to have something simple and quick and efficient and stable. You don't always get that in one algorithm. So that's as far as we'll take it today. We're going to use that algorithm shortly and study how good it is and compare it to the bisection method and some of the modified methods. And you'll also have a chance pretty soon to try some of this in homework and do your own comparisons of how good you think it is. With that, we'll come back next time.